Today we'll be discussing about the derivation of transmission line equations for voltage and current. Basically, this is a very important question because so several times the question has come. So this is a derivation for transmission line equations for voltage microwave transmission line, basically not the normal one. So we have to understand microwave transmission lines are different from the normal transmission lines. So what I do, it's in getting autoplayed. So yeah. So since there is no tool for me to write the equation, so I have picked up from the notes itself. But in the notes, I have observed certain corrections. So what I did, I have using my technique. I have corrected several parts wherever there were some issues were there, some observations were there, some corrections were there. I have corrected it and have converted into JPG and pasted onto the your PPT so that you can able to appreciate the this thing. So with this, actually I have done some pre-recording yesterday. So with the voice, but the voice was not clear. So that's why. Now you can see the slides will be moving here and there. So I'll be requesting you to adjust with this. So microwave frequency. Now otherwise I'll go out of the show, and it will be a little smaller one. That's why I take out the narrations. Okay, let it be there because it will waste the time. Yeah, I'll be moving here up and down so that to make it easy to, it's automatically moving. So I will revert back. The microwave frequency starts from 1 gigahertz to 300 gigahertz. In transmission line theory, the losses throughout the length of the transmission line depends on its length and wavelength of the source signal. We all know this. And then the length, if the length of the transmission line, that is L, is lesser than lambda, that is the lambda wavelength of the your input source, then what happens is the transmission line has got no losses. Generally, if the condition satisfied that your length of the transmission line is lesser than the wavelength of the source, then there will be no losses. This is for the normal case. So therefore, we also have R is equal to 0. That is, the resistance will be of the transmission line will be 0, and the conductance also will be 0. Now, if you consider one example here shown, now this an example here, a AC generator is there. This is a source, and which is having a frequency and voltage. VG is the voltage, and the frequency, some frequency, source frequency is having. And we also have this source impedance. Every source has got certain impedance. So this is the source impedance. Let us say ZG. Now this is the transmission line. So you have a transmission line in between connected, and we have a load impedance. This is load impedance. We connect load, no? We connect some kind of load to always a source and load and the transmission line. Then we have the source impedance also. Now this, let us say, now how much would be the now in this case you see if the condition is length is far lesser than lambda. Now here wavelength is we know that wavelength is given by C by F, where if I consider the F is equal to 10 kilohertz, if I consider the source frequency of 10 kilohertz, then what would be my transmission line length? If I have that, then I can calculate length lambda is equal to C by F. We all know C is equal to 10 to the power of 8 by 10 kilohertz. If I do calculation, missing little bit. Now it will come to around 3 to 10 to the power of 4 meters, which will correspond to 30 kilometers. That means my transmission line length of 30 kilometers for 10 kilohertz of frequency. So this is what is the calculation which is done here to make you understand how the microwave source and the normal source difference. Now that was the normal source. Now in any communication laboratory, the connecting wires used between source and the load circuit is having, it's depend very much less than the 30 kilometers. That means L is far lesser than 30 kilometers in laboratory. But now therefore we can say that L is very much lesser than lambda. That is, L is far lesser than lambda. Therefore, no losses in the transmission line. And whenever we are doing such things in laboratory or somewhere, there will be no losses. And to find the load voltage, we can use a normal circuit theory, that is voltage divider rule. There is something called voltage divider rule. When you apply this thing, V load, that is voltage, load voltage is equal to Vg into, that is source voltage into source impedance by ZL, load impedance plus source impedance. Sorry, this is load impedance. That is voltage, source voltage into load impedance by load impedance plus your source impedance. So this is the your voltage which divider rule is. So in all microwave systems, the frequency range is approximately from 1 gigahertz to 300 gigahertz, and this extends up to thousands of gigahertz for video band. We all seen that frequency band going up to 300 plus gigahertz and applications and all. So at microwave frequencies, the length of the microwave transmission line, that is L, becomes far greater than wavelength because of my high frequencies. Now, therefore, the voltages and currents become the function of length of transmission line. Now, in the normal case, L, length of the wavelength lesser than lambda, the length of the transmission line lesser than, far lesser than lambda would have been the normal case. But since, okay, the slide is moving automatically, I'm coming back again. So this is because of that yesterday I did some practice for video. I wanted to share a video on this, but I could not succeed, but the video audio quality was not good. Therefore, the voltage and currents also become function of the transmission line. Now, this is very important. Now, in the normal case, when length is far lesser than your wavelength, when the normal, other than microwave transmission line, what happens? Your voltages and currents will not come into picture. So, what happens now? The moment you go for microwave frequencies of the transmission line, then you have to derive, and equations become different. Equations are different, totally different. Voltage and current equations are, the voltage and currents are included in the equations. So all that things we see. Now, consider a microwave transmission line. Now, that was a typical, normal, conventional transmission line. But now we consider the microwave transmission line. So consider a microwave transmission line having a length of L connected between generator and load. Now, this is a generator or a source, and this is the load, we all know. And similarly, we have input impedance, that is source impedance, ZG, and also this is a small portion of the transmission line, what we call about. This is the transmission line in between the source and your load. So this, we consider this as a length of L. When we have a length of L transmission line, then in that we can consider a small portion dx or dz. Dz would be the small portion of the transmission line within the, it's a section, small section for doing the calculation purpose. So what I'm doing here, I'm taking a source and load, then this is the source impedance, then we have length of the transmission, and this is the total transmission line I'm talking about. And then we, in that whole length, I consider a small portion of transmission line, dz. So then we do some analysis here. So at microwave frequencies, the length of the transmission line, as we know, L is far greater than lambda because it's a microwave frequency. So what happens is, we know lambda is equal to C by F. F is very large in gigahertz. Therefore, we get losses along the length of the transmission line. We all know when we are doing experiments in the within the less than 30 kilometers for low frequency, that is 10 kilohertz, we found that there were no losses. The moment length of the transmission line increases or the frequency increases, the losses actually occur along the transmission line. When we have transmission line losses, it is undesirable. We have to calculate how much would be the, what would be the losses, what kind of losses will be there, how much would be losses, all that we have to calculate. So therefore, what we do, we consider a small section of dz of the microwave transmission line as shown in the figure. Now this, as we told in the last figure, we have shown small dz was considered. Now the small portion within the transmission line, the same small portion of the transmission line I consider, that is dz, which has got again all that thing. But now within this, if you consider, and if you draw equivalent circuit of this small transmission line part, what happens is you find so many things are there within that. One is the resistance, inductance, admittance, capacitance, everything is there, transconductance. So all these three factors we have to see. Now this, now see, you can see from the figure, the voltage and current parameters which are linked to this transmission line. So that has to be, you have to calculate at the microwave frequencies. Now in this case, we have resistance R in ohms per meter, this one R, and inductance L in Henry per meter, this one, and then conductance G in mho per meter or Siemens per meter. This is the your conductance. Then we have capacitance, that is C in farad per meter, this one. So all these things are in the part of the transmission line. This is the transmission line, microwave transmission line equivalent circuit for a small portion of element which we consider in the transmission line. This is not the full length of the transmission line, but a small portion DZ equivalent circuit. So all the four parameters are function of length of the transmission line. So I'll be coming back again because there is some issue. Yeah. I hope everyone can listen to me. Saurabh?
Yes.
Oh, okay. I was asking because suddenly we don't know when the
Yes, sir.
Get cut out. Okay. Now, therefore, the parameters are called as lumped parameters. Now, all these parameters, that is resistance, inductance, conductance, and capacitance, all these are called as lumped parameters of a microwave transmission line network. See, there may be a question. BTU may ask you a question called, what are the lumped parameters of a microwave transmission line? Please don't get confused. Don't get hassled. Just draw this figure, and explain what is resistance, inductance, capacitance. That's all. You will get 4 marks. That's all. Simple. So don't get confused because lumped parameters we never, because they just try to, sometimes they want to make it, very difficult question like that. So please consider this. Now there is something called line impedance. Along with that, we have line impedance. What is line impedance? This is your line impedance. That is one resistance and your one inductance which is there. So this forms a part of a line impedance. Okay, you should understand in the transmission line, microwave transmission line, what are all these parameters? This is the line impedance. This is called as a line impedance. This portion, one resistance and one inductance. We all know resistance is denoted by your R and inductance is denoted by JXL. So what whole, if you combine, what happens? The whole Z is equal to R plus J omega L ohms. So we know that it's a combination of line impedance will be given by R plus J omega L ohms. So with that, now the reactance of the inductor is given by XL, which is omega L. We all know, we have studied in our class 12. So angular velocity, angular frequency, that is the omega is given by 2 pi f, where f is the frequency. Now the line impedance of the transmission line becomes Z is equal to R plus J omega L. We know this. We have just substituted J omega L here. Now this is the one of the parameters for understanding the transmission line. Then we have line admittance. There's something called line impedance and line admittance. What is line admittance? The parallel part circuit which is there. We had one series and one parallel. So the parallel one consisting of capacitance and your conductance is called as line admittance. Now it is measured between the line in parallel network. Now this is given by, we know G and 1 by JXC capacitor. So it will be given by J omega C, or XC is equal to 1 by omega C. We all know this capacitance if you see. Okay. For parallel circuits admittance, calculations are used. I am just following your notes. What happens is, if you follow the notes, it will be very easy. And whatever I am telling, it will be correlating with your notes. So it will be very easy to assimilate, understand, and reproduce in the exam. That is why I am doing this. Otherwise, I could have used a board and all, but it may not be visible for you. So you may have problems in understanding also. Now here, Y is equal to G plus J omega C. We all know mho or Siemens. This is your line admittance. Then we have characteristics impedance. See, understand, so many things are there. Characteristics impedance. Now it is the line impedance along the length of the transmission line, which is denoted by Z0. Now that means we know line impedance, we know line admittance. When I know both Z and Y, I can calculate your Z0, that is characteristics impedance. What is the characteristic impedance? Is given by square root of Z by Y. That's all same. Line square root of line impedance by line admittance is your characteristics impedance. This is very important. This has come so many times. What is the characteristics impedance of a transmission line? The question may come. So what you say, for that you have to write these two. You have to write you have to write other parameters also. This line admittance you have to little bit explain. Slide is moving automatically. I don't know why. Yeah, okay. So I hope it will not move now. Yeah. So when we have characteristics impedance, which is square root of Z by Y, so I can represent as replace Z by R plus J omega L and Y by J plus J omega C. The same whatever we have derived here. When I put this, now why I'm doing this is I want to see what will happen to my transmission line if my characteristics impedance has got some value. So we have something called characteristics impedance. Also, we have something called load impedance. For a perfect matched transmission line, if my transmission line has to work properly, without any losses, it should transmit. For that, there is one precondition that my Z0, that is characteristic impedance, should be equal to the load impedance. That is one of the prerequisite conditions. If I have Z0 is equal to ZL, then only I'll be able to transmit whatever I have produced in the generator to the load. Otherwise, I cannot have a proper matched transmission line. If I have ZL equal to Z0, then only I'll be able to produce a whole generated input to the output load. That is what is required. So your characteristics impedance will become very important in case of a transmission line. Now, considering a mismatched load, let us say that the source impedance, that is characteristics impedance, is not equal to the load impedance. We all know what is characteristics impedance. We know characteristic impedance is defined by your Z by Y, that is line admittance, which is a series network, and divided by the line admittance, which was the parallel network. So when I divide those, I'll get the characteristics impedance. Now this characteristics impedance, if it is not matching with the load impedance, then what happens? When the impedance are not matching, then you will have a reflections occurring in the transmission line. That means what is happening? What I'm trying to do here is I'm trying to send a signal from here to here outside. But because of the losses in the transmission line, there are reflections because of the characteristics impedance is not matching with the load impedance. What happens? The wave, instead of going out, it will reflect back. If you have that thing, that means your purpose is defeated. That means whenever you are having a load mismatch, you will not be able to transmit the signal to the load, or whatever you are trying to send in the transmission line, you are not be able to achieve. That means matching the transmission line is very important. That's why we call it as, if transmission line is not terminated with the characteristics impedance, then it is said to be a load mismatch. When there is a load mismatch, that means when ZL is not equal to Z0, that means when load impedance is not equal to the characteristics impedance, there will be a mismatch, which will lead to reflections in the transmission line. Whenever we have reflections, we will not be able to transmit in the transmission. Main purpose of the transmission line is to transmit the signal. So when we have such reflections, you will not be able to transmit the signal. Sorry. These are the basics about the transmission line. Now we come to the main content. That is your transmission line voltage and current equations. Now there are so many times VTU has asked questions. Derive line voltages and currents with respect to transmission line, starting from fundamentals. Obtain the current and voltage equations along with its solution for all for microwave transmission lines. This question may come. This is very important. Now we derive these equations for voltages and current. Please bear with me. I may have to go through these notes only, because these are the corrected notes. Please don't take the notes which is available in the website. I will be forwarding these slides. Please follow that, because there are certain corrections, and those corrections I will highlight here, whatever corrections I have done, so that don't get it's a very minor corrections, not major, but you should not repeat those corrections, same wrong equations there in the exam. Okay, now we'll derive the transmission line voltage and current. Now because I'm unable to use the mic for writing the equations, so I'll be preferably using these slides. This is the best method, I thought, because I don't have any board. I have board, but if I use that, then you will not be able to see because of a lot of other issues. But anyway, okay. And I have what I made. I have during this thing IAF, I have made certain videos on this transmission line. I have conducted classes for all my engineering students, engineering officers. So those videos also I'll upload. You can correlate. It is almost same. It is as good as notes only, but in the video format. One of my friends has explained clearly in that. So you can use that videos also. So I'll be posting those videos also. Since my network is okay now, so yeah. Now we'll consider this circuit. Now this is. I hope I am there. My connection is okay. Saurabh. Saurabh.
Yes, sir. It is very clear, sir.
Oh, thank you so much.
Thank you.
Are you able to understand? Follow now till now? Is there any problem with students? All students are okay with this?
We understood,
okay,
sir.
fine, good. Please, if you do not understand, please let me know so that I can repeat question. And also, I'll be followed up by the video. I have done some videos with my friend. I will be uploading it. So it is almost close to the equations. So it will never have anything which is missing in these equations will be covered in that video. That also I'll give you. Do not worry. Do not get hassled because this is a very important question. It may carry for 12 marks derivation. So be careful. So now consider a transmission line having a length of length far more than lambda. Why this is far more than lambda, Saurabh? Why this condition is there? Saurabh, why this condition is there? Length of the transmission line far more than lambda.
So because the wavelength is less, like the wavelength of the wave which was.
But because of the microwave frequencies.
Yeah.
Because of the microwave frequencies, it is there. Otherwise, if it is a normal frequency, low frequency, then it would have been length would have been lesser than far lesser than lambda. Okay, this is very important. This is the prerequisite condition you should always remember. Okay, for microwaves, it is always the transmission line length is far greater than the wavelength. This is please keep it in mind. Okay. Now coming to the circuit. Now we'll go to this is a generator, a small generator with a source impedance of ZS, and also we have a transmission line, and we have a that is a load with impedance of ZL. So now the length of the transmission line is L, and L is far greater than lambda. And also now please concentrate here. This is the small portion of the transmission line. This is the full length transmission line. Okay, from here to here it is full length. Now here I consider small amount of transmission line as I considered earlier, delta Z, small amount of transmission line I consider. When I consider a transmission line, the starting I can represent here as Z is the starting point, and after this transmission line, when I go here, it will become Z plus delta Z. So this is the distance what we talk about. So at this point is the point Z, and we have distance of delta Z because this is the small distance which is there. And so at this point, now it will be Z, this for this point plus delta Z will give you the distance at this point. Now we have a load here, and we'll go further now. So consider a small section of the transmission line having length delta Z, that is delta Z, at as shown in figure. It is equivalent. Now if I draw the equivalent circuit of this thing, now everyone has followed. Now last we have derived. Now see again, this is the voltage. There's I and T, then R delta Z, because delta Z is inward. So this is delta Z. So I will wherever R is there, I will also include delta Z also. Now this is the current I of Z and T. So I'll put with respect to T also, and also I have inductance L delta Z. And now what is this called as, Saurabh? This whole thing is called what? This is called as line impedance. Correct? No.
Yeah, the sum of
line admittance. The series is line impedance, and the parallel is the line admittance. Okay. Okay. Fine. Now I consider one point A, and this is the G delta Z accordingly, and C delta Z capacitance. Then voltage at the output. Now at this point I have a current which is Z of Z and T will become now I of Z plus delta Z, because now delta Z is included, because that your small amount of delta Z is also included at this point. So this Z plus delta Z and T. So this equation all will get modified to the Z plus delta Z T and all. So we have this is the length of the transmission line, that is small amount delta Z. So this is the part of the transmission line, small section dz. So when we do this, now hold on. Some slides are moving automatically. Wait, okay. In microwave transmission line, the current and voltage are functions of distance and time. Now this is very important factor. In microwave transmission lines, current and voltages are functions of distance and time. Now in the figure we saw current and voltages are at a distance Z, that is starting point, and at a distance Z plus delta Z, ending point of the small section of the transmission line. So we saw that. Now the current equations for the transmission line can be given by applying KCL. If I apply KCL at node A, we saw the node A. Okay, if I apply KCL, that will result into I into ZT, which we the initial current. Then we have IJ plus IC, which is actually this is equal to actually this is small one. Ig plus Ic, that is your conductance and capacitance. Then I of that current is also there, where our output current, Z of Z plus I of Z plus delta Z into T. So this whole thing is now we are equating it. Now when we equate it, we convert it into now little modification we do simplification, we get this equation. When we get this equation, we convert this equation into your delta Z and admittance, and we put that capacitance because the current, no, this current we have to convert it into your voltage and other relations. When we convert, we will get this equation. So this equation, if you want, you can see the video. It is clearly presented. I will give the video. Okay, in the notes it is not clearly stated how they have converted it, because it's simple. Ig, for Ig, this is the voltage equation which is there, because we have that admittance and the voltage, we convert into Ig into voltage, Ic into voltage, because capacitance we know d by dt of voltage. So of that Z plus delta Z. So that's simple. We have studied already in your engineering first year, second year. That all we have studied. Now, after opening this equipment, if you want any details for this, video it is covered fully. I will give the video also. Now, what we do, we divide throughout by delta Z and apply limit Z tending to 0. When we do this, what happens? Now here, eventually, I of Z of T, all these things I apply, I divide throughout by delta Z. Now, wherever delta Z is, it gets cancelled out, and Z is tending to 0. What happens is, I remain with change in the I. There's a difference of I, which is the delta I by delta Z. Delta Z will remain, which is equal to this portion will get eliminated because Z is tending to 0. These two portion will get eliminated. So we remain with GV, that is minus sign is there, so minus will come. GV will come here, and then C dV by dt. C dV by dt will remain. So this whatever within the bracket will go off. So this will remain. Now in terms of admittance, if the same thing can be written as di by dz, which is equal to minus of G plus J omega C into V. Similar, but in the admittance it changes. In the capacitance it is C dV by dt. For in inductance it is a difference. So you have to change it accordingly. In the voltage and current we have written like this. Similarly, when we apply KVL, we get it is a KCL we applied, so we got di by dz and we got this equation. Now, if I apply KVL, we get dV by dz, which is equal to same minus of R plus J omega L into I. So similar, same equation, but in terms of inductance and resistance. Here it is admittance and capacitance. In terms of voltage, current, voltage, inductance, capacitance and conductance. Now here voltage in terms of resistance and inductance and current here. So this is what we get equations. Now these three equations, that is the equation 3 and 4, that is Rj omega L represents total impedance of the microwave transmission line. Now that is what we call Z is equal to, we all know that Z is the total impedance, that is R plus J omega L, and G plus J omega C represents the admittance. Simple. Z is impedance, Y is your admittance. We all saw that even that in the previous line impedance and line admittance. Whatever was it, resistance and inductance was the line impedance, and whatever in the parallel circuit, that is Y, that is G and C was there. So that was your admittance, similar to that. Now, with this, from the equation 4, what I can write is, I rewrite the equation, same equation, I is equal to minus 1 by C, don't get confused. Equation 4, where is equation? This is equation 4. I will write in terms of I is equal to what? dV by dz divided by your R plus J omega L, correct? No, minus will go that side. Similarly, I can just write I is equal to minus 1 by R J omega L into dV by dz. So this will become equation 5. Now when I substitute this equation in equation 3, I will get dz by d by dz of that whole term is equal to minus G of J omega C V. Now this equation will become a new equation like this. Now if you take out this thing, now dz, this is all your constant. So dV square by dz. So we just take it out. So this will be like, you take out this whole thing out, d square V by dz square. Now this will become, and this is equal to same, this will remain same, J omega C into V. Now we know d square V by dz square is equal to, I will transfer that side. So minus will get cancelled. So R, there is R J omega L into G plus J omega L. G omega C into V. So this will be a equation you will get. But here we know that propagation constant of a transmission line is given by gamma, which is nothing but this d square V by dz square. This is the one of equation we have. So we know that d square V by dz square is a gamma square V. So if we equate this similarly, and in the notes here I want to highlight, please understand, in this equation we have seen in the notes here it is some correction is there, so that I removed it. I have made it very neatly. I have corrected it here. Okay. Now at this point of time, d square V by dz square is your lambda square V, which is equation 6. Similarly, decoupling 3 and 4, again same we can get in terms of current. Now this is voltage, so d square I by dz square is equal to minus of G plus J omega C into R plus J omega L into I. So this we get like this. And in terms of, so if you this thing you can see similarly, if you equate this thing, instead of voltage here, now you get in terms of current. Now here we got d square V by dz square is equal to gamma square V. Similarly, we get d square I by dz square is equal to gamma square I. So these are all, these two equations are very, very important. So these three equations are called as transmission line current and voltage equations, so which you have derived. So this finally you have to get this. So when we equate this, you in this when we show where this gamma represent the propagation constant, there may be a question, obtain an expression for propagation constant of a transmission line. This is nothing but a transmission line equation for voltage and current, and in that you equate for the voltage and current like this and show the equation. Now these are the equations, so I can write gamma square is equal to, because of gamma square we know R plus J omega L into G plus J omega, so gamma will be the square root of this whole term. In this, when you equate this thing into terms of that real and imaginary part, so this will become gamma is equal to alpha plus J omega, alpha plus J beta. So now when you see equate all this equation like this, now in this part alpha will become attenuation coefficient of the transmission line or attenuation constant, and then beta will become the phase constant. So don't get confused, don't get hassled. In case if a question comes, please define attenuation constant and phase constant of a transmission line. Simply you write this propagation constant formula. In this formula you equate it to alpha and beta. You say alpha is the coefficient of your attenuation constant, and beta is the phase constant in a transmission line. So simple. If you show this, this will get marks. It may be question for 2 to 3 marks. That's all. Okay. Now, after obtaining the equations for transmission line and voltage currents, now we have to find a solution for that. Now it is not that only you, because you have to find, the question is that derive an expression for, please understand the question, everyone, please be careful in this question. This is a very 12 marks question. They have asked you to derive equation for transmission line voltage and currents, and also find the solutions for those equations. So you have to derive the equations. That is what we have done till now. Then you have to find the solutions for those equations. How to find solutions? We know that consider voltage equation 6 of transmission line, that is d square V by dz square is equal to gamma square V. When we consider this, you simply take term this side. So dv square by dz square minus gamma square V is equal to 0. This is another equation. Yeah. Now, if you take the roots of the above equation as per your mathematics, basic mathematics, engineering mathematics, so d square minus gamma square is equal to 0. So that means we have d plus d is equal to plus or minus gamma. This is as per the root of the equation. Now for this, I don't want to do the solution here. If you are capable of doing it, it is your basic mathematics, engineering mathematics. Apply those solution. So if the solution for that d is equal to plus or minus gamma will give you v of z is equal to v plus e to the power of minus gamma z plus v to the power of minus e to the power of minus delta gamma z. So this will be your equation, solution for this equation. Now where v plus and v minus are the constants. These two are the constants. So these are not don't consider them as things. These are the constants. Now similarly, the solution for the current equation is given by Iz is equal to I plus e to the power of minus delta z plus gamma z, plus I to the I minus e to the power of gamma z. So this is equation 10. So these two equations you have found, where again here v plus e to the power of minus delta z is a forward voltage, or the incident voltage at the load, and V minus e to the power of delta Z is reflected voltage, backward voltage, which is reflected from the load. In a transmission line, we find if the transmission line is not matched, then what happens? There will be reflected voltage. Every transmission line will have some amount of reflected voltage, some amount of the forward voltage. Every transmission is not 100% sure that it will not have any reflected voltage. There is no transmission line which 100% matched load. So there will be little bit reflections will be there practically. So considering all above equations 9 and 10, the solution of the transmission line voltage and current, the ratio of V plus and V minus and I plus and I minus indicate characteristics impedance of the transmission line. That means Z0 is given by V plus by I plus, or for the reflected wave minus V minus by I minus. So which will correspond to our, if I compare with the previous equations, that will correspond to Z by Y, that is line impedance by line admittance. So I can write this equation as R plus J omega L by G plus J omega C, that is ohms. So this is the characteristics impedance equations we have equated. All your current and voltage functions have been included in this. So finally we can say that in voltage equation of transmission line consists of incident wave, forward wave, and the reflected voltage. That is incident voltage or reflected voltage. Now incident voltage at the load is given by same V is equal to e to the power of minus gamma Z, which is Vi. Now in the notes you have to be very, very careful here, because at certain point they have given incident and at the certain point they are given see, in this case if you see here, it is incident voltage V plus. Here the incident voltage is V plus. Yeah, it is correct. But I have made some corrections. Earlier it was some wrong they were given. So we have to be very careful while handling. See here it is reflected voltage V minus, but it is shown only V. See, all these things we have to be very, very careful while writing the equations. Now coming to the derivation of reflection and transmission coefficient. Now there will be a question like, what is the reflection coefficient of a transmission line? This is also very important. Expression, derive an expression for reflection coefficient in terms of your load impedance and source impedance. Some question will be there like that. So what you have to do is, now definition is, reflection coefficient means if the transmission line is not matched, so some amount of energy or the wave voltage will be reflected back to the source. So what is that amount of reflection which I'm getting reflected? So that is what is called the reflection coefficient. It is measured in terms of reflection coefficient. So it is the ratio of the reflected voltage at load to that of incident voltage. So please understand, this is very important terminology. Eventually you have to write this in terms of the formula and the definition. So now we have reflection coefficient is given by VR by Vi, the constant dimensions quantity, where Vi is the incident voltage at the load, which is nothing but V into e to the power of minus delta Z, gamma Z. And then we have R, reflected voltage from the load. It is at the load, from the load. Please distinguish this. V into e to the power of gamma Z. So this is the vector quantity, complex number. It is the value depends on the characteristics impedance of the transmission line, that is Z0, and load impedance ZL. Now this we know, this is given by ZL minus Z0 by ZL plus Z0. This we have to prove. Now in terms of, you have to prove this expression. So how to go about is, now consider this a transmission line, which is called as the, now we can say, expression of reflection coefficient in terms of load impedance and characteristics impedance. So this question will be there. Derive an expression. First of all, they'll ask, define what is reflection coefficient, 2 marks or 3 marks. Then derive an expression for reflection coefficient in terms of load impedance ZL and characteristics impedance Z0. I hope I'm there in the connection. Hello, Saurabh. Saurabh?
Yeah, yes, sir. You are there in the connection, sir.
Okay. Following it, na? Are there any issues? Are there anything which is not understood?
Nothing so far, sir.
Okay, fine, thank you. So going further, now this what is there is, now again I am considering the transmission line. See, now what I'm doing, please understand here, to understand reflection coefficient. Reflection coefficient is nothing to do with the source impedance. So we will only concentrate on the load because the reflection is happening from the load. You can see this is the transmission line. This part was the source, which I have removed it. Only I have considered a transmission line with the load impedance and the length of the transmission being L is equal to Z. And we have the characteristics impedance also here, Z naught. And here load impedance, ZL. We can see one wave which is going VI and one voltage which is coming back VR, reflected. Forward voltage, reverse voltage, that is reflected voltage. So we have this incident voltage and reflected voltage. Now we will derive the expression for how much will be the reflection coefficient, how much reflection is occurring in this load. That is what I have to derive. Please don't get confused with other coefficients. Reflection coefficient means amount of energy which is reflected back to this side. So that is what I have to calculate. So for that, what I do, I consider a transmission line having characteristics impedance Z0 and load impedance ZL. So when I consider this, now this is the length of the transmission line, which is L is equal to Z, from 0 to Z, you can see. So we draw this transmission line equation, circuit. Then from the definition of the reflection coefficient, we know that we know that it is VR by VI, that is reflected voltage by the incident voltage. Now here there is a correction in your notes. Please refer to the notes, page number 9. Here I have corrected it. Actually, there it is mentioned incident voltage at the top, reflected voltage at the bottom. So I have corrected it. Now this is the reflected voltage and this is the incident voltage. So this makes a difference actually. When you write wrong equations and label the parts, then you will land up in a lot of problems. So before taking into any kind of notes, you have to assure that 100% sure that all equations are correct. So please correlate with your notes, and whatever is given in the slides are corrected to an optimum limit. So now considering the load impedance ZL is connected at a distance of L is equal to Z. We know that, no? In the circuit we saw L is equal to Z. Length of the transmission line is Z of the transmission line. So we can write that is load impedance equation. That is ZL is equal to VZ, that is voltage VZ by IZ. Simple. Whatever is there, V of Z into I of Z. We know that the voltage and current through the transmission line at any distance is LZ is given by VZ is equal to, we know that we have already proved it, V plus into e to the power of minus, we have found the solution, no? V of Z is equal to V plus e to the power of gamma Z plus V minus e to the power of gamma Z, which is called as equation 3. And similarly, in terms of current, it will be I of Z is equal to I plus e to the power of gamma Z plus I minus e to the power of gamma Z. So this is equation 4. So with both equations, the characteristics impedance of the transmission line becomes Z0 is equal to V plus by VI plus. We know that, we already proved this. So I plus, where I plus I can write it as V plus by Z0, just simple calculation. And then we have Z0 is equal to, in terms of reflected voltage, we have minus VI by I minus. Then I minus is equal to V minus Z0. Same, just simplify. Then when we write the equation, we know I of Z, that is in this equation. This equation, I of Z is equal to, if I substitute the same values in these equations, so what happens? I get this equation. So Iz is equal to V plus by Z0 into e to the power of minus Z, V minus by Z0 into the power of gamma Z. So similarly, I take Z0 as common, 1 by Z0, then the equation becomes V plus e to the power of minus delta Z minus V minus e to the power of delta Z. So this equation we'll get when I substitute all these values in these equations. Now what I do, divide 3 with 5, we get what? Divide by simple. See, we have V of Z is there, and we have I of Z. So we have calculated I of Z in terms of this voltage, and finally we have V of Z already there. So I divide V of Z this equation by IZ. So what happens? I get what actually done is I have converted this I of Z in terms of voltage. That's all, because I want to divide here. I have converted this I of Z in terms of voltage, in terms of this like this. So you can see I of Z is converted into voltage terms. Already we have V of Z in terms of voltage. So when I divide, it will be easy for me. That's why I did. So when I do this, V of Z by I of Z, we'll have V plus into E gamma Z plus V minus E gamma Z by 1 by Z0. Same here, whatever this term is there, it will come here. V plus e to the power of gamma z, V minus e to the power of gamma z. So when I do it, simple calculation, we know Vz by Iz is ZL, that is the load impedance. Now, which is nothing but once it is in the numerator by numerator, so it will come up the top on the front side. Now, hello, Saurabh, are you there? Something happened. Saurabh?
No, sir, nothing happened.
I had some like sound, the disconnection sound. Okay. Oh, okay. I'm a little worried now because got used to that disconnection. Okay. Now Z0 is there. Now Z0 will come on the top. So you just write this equation as it is, just like that, and also write this equation as it is. Now here, what in the main notes, which is in the college in the website, please refer. There is a correction in that. I have made this correction. Now I have now here I am in this equation I am dividing throughout by V plus E gamma z. This term I am dividing numerator and denominator. So with that, what happens when I divide same term by same term, this will become 1 plus V minus e to the power of gamma z by this term, that is V plus e to the power of gamma z. Then in the numerator, the denominator also, this is divided by a whole thing, which will become 1. Instead of plus, it will become minus because it minus is here. So now this becomes V minus e to the power gamma by V plus this thing. So I divided that thing, whole numerator and denominator. With that, what happens? But this term in main notes of the college, there is an error. So it is reverse actually. So please correlate and accordingly you will make the corrections. So I have corrected in this. So that's why you should not get confused. But if you refer to the college notes, then there is some issue in that. So please be careful with that. With respect to reflection coefficient, I can write ZL is equal to, so what happens? We know that this is the reflection coefficient actually. This portion, this portion is the reflection coefficient. We know that there is V minus by e to the power of delta z by V plus e to the power of delta z. We have already proven that. So finally, when you substitute this thing in this, so what it becomes is ZL is equal to Z0 into 1 plus the gamma z reflection coefficient by 1 minus that is your reflection coefficient. So when you do this, you get a new equation now. So new equation. So what I do, I will do a little bit simplification. I will just convert it, send it to the numerator, and do a little bit here and there, left side, and rearranging the terms. I get in terms of this, if I take it, then what happens? It will ZL by Z0 by ZL by Z plus Z0. That is load impedance minus characteristics impedance by load impedance plus characteristics impedance. This is your reflection coefficient equation. So this is dimensionless. Now here with this equation, I can now clearly see for if ZL is equal to Z0, that means if the load impedance is matching with the characteristics impedance, then the transmission line will be perfectly matched. Now you have proven. How you have proven? With the equation you have shown that if ZL is equal to Z0, then the reflection coefficient becomes 0. When the reflection coefficient becomes 0, that means there will be no reflection of voltage from the load. Simple derivation. We have obtained this. So till now we were saying that if the reflection coefficient is 0, then voltage is 0 from the thing. So there will be no reflection. But we have proven it in terms of equation. So we are, with the evidence, we can show that when I have ZL is equal to Z0, then it will be reflection will be 0. If in case ZL is not equal to Z0, that means if the load impedance is not equal to characteristics impedance, then the transmission line is not matched properly. If the transmission line is not matched properly, then there will be reflections. So how much will be reflections will be given by some magnitude and some direction. So that will be expressed in polar form or your rectangular form. So which will be given. So where modulus of this thing, reflection coefficient given, magnitude of the reflection coefficient, and there will be some in what direction. See, this is a vector quantity. So that's why you have to be very careful. Reflection coefficient is a vector quantity which has got magnitude and direction. It is not a scalar property. So that's why, because both some quantity, the magnitude is also there, and also it is moving in some direction. Reflection means it is getting reflected, but in what direction this is getting reflected, we don't know. It may be towards source, it may be towards 30-degree offset from source. So that direction is given by your theta. So always your reflection coefficient will have magnitude and theta. So now this reflection coefficient is measured at the load, is also called as load reflection coefficient, and is also denoted by your load, that is your this term, okay, gamma L. Now come to transmission coefficient. Till now we have studied about the reflection coefficient. That means how much a transmission line can reflect energy. Now we see transmission coefficient. Now how much the reflection, that no reflection, but the transmission line will transmit. How much it will transmit? How much the transmission line will transmit the voltage? That is what is called as transmission coefficient. So the transmission coefficient of a transmission line is defined as the ratio of the transmitted voltage to the incident voltage. So now this is simple. In terms of reflection coefficient, it was what was that? Incident to the reflected voltage. Now here it is transmitted voltage to the incident voltage. Now it is the ratio of the transmitted current to the incident current, similar in terms of voltage and in terms of current. Both are same. So now we consider here the same the circuit, the load impedance. Now what happens here is reflection coefficient, we also consider the same circuit, but here what is happening is we have to transmit the whatever signal which you are available at this load to other transmission line which is attached to this. So it is that we are actually forwarding the voltage or the signal to the other transmission load. So here the voltage is not coming back but is going forward. So that is what we have to consider. Now that means I can write transmission coefficient as tau is equal to Vt by Vi. That is the voltage which is transmitted, that is load, that is whatever is in the load. Vt is equal to VL. Whatever in the load voltage is the transmitted voltage. And we have incident. What is that? Is that, see, there are three things. One is the voltage which is incident from the source, and voltage which is reflected from the source, load, and the voltage which is at the load. So now in this case, the transmission coefficient means the ratio of the load voltage or the transmission voltage to the incident voltage. We will not consider VR here. VR is nothing to do, but we may consider in your equations to solve the equation. Transmitted voltage from load to next section. Transmitted voltage from load to next section of the transmission line is equal to, now we have to consider here a lot of voltages, which is given by Vt. That is Vt is equal to VL. Vt is equal to VL. We know that. Which is also equal to, what is Vt? Vt is nothing but incident voltage is also there, and small amount of reflect voltage is also there, which is very small in this case. But it is not 100% that you can't say that there will be no reflected voltage. There will be small amount of reflected voltage is always there. So when we consider this equation, so what happens is your tau is equal to, that is transmission voltage coefficient is equal to Vt by Vi as per definition. So when we know that Vt is equal to Vi plus Vr, Vi plus Vr by Vi, when we do it, so simplify it, 1 plus Vr by Vi, which is a, we know Vr by Vi is nothing but your 1 plus gamma. So tau is equal to 1 plus gamma is your transmission coefficient equation. In terms of ZL and Z0, characteristics impedance, and always whatever you do, you have to equate equations in terms of load impedance and characteristics impedance. Very, very important. So transmission coefficient in terms of load impedance and characteristics impedance will become tau is equal to 1 plus gamma. We know gamma is also equal to 1 plus ZL, that is ZL minus Z0 by ZL plus Z0, which we already proved. So when we put a little bit, do some simplification here, when I take the LCM and all other things, then I obtain 2 ZL by ZL plus Z0 is your final derivation for transmission coefficient in terms of load impedance and the characteristics impedance. So this equation is derived. Now this full equation you may give you 6 marks. Definition, what is transmission coefficient? Derive an expression for transmission coefficient of a transmission line in terms of characteristics impedance and load impedance. This question will come for 6 marks. So simple equation, very simple. You just write, very easy, and you can always draw small circuit like this. You draw this circuit and explain. You will get 6 marks in the exam, 100% marks. Standing wave ratio. Should we stop or should we continue? Saurabh?
Sir, I think we can continue tomorrow.
We can continue tomorrow?
Yes.
Okay, okay. Now, please switch on your videos for some time. I would like to interact a little bit. Please switch on, all of you, please switch on your videos. या शर्मा जी कैसे हो? समझ में आया पूरा क्लास? I hope you
Yes,
understood.
sir. Yes,
Because
sir.
I have clearly explained as per the notes, because it should not cause problem for you. Because the notes is already there. Little bit a correction I have done in the notes. So kindly correlate with the notes. But whatever available in the notes have got some errors in that, which I have corrected, and I'll be sharing these slides. Please follow the same slides because there are corrections. You can, if you want, you can cross check with the available notes which is there, and accordingly you can make. Now I'll be giving you videos also, which we have made in our IAF and all. We have uploaded already. Those videos are available on video of YouTube because we have conducted some training program in our Air Force, and we have conducted for civilian agencies also. Some DRDO and all we have conducted. So those videos I have downloaded, and I'll be sharing with you along with the slides. You can correlate with this thing, and you don't get confused. Follow one. That's why, to make it easy, I have derived equations which is there in the your college notes only, because it will, otherwise what happens, I can take from so many other sources, but that will clutter your mind. I want that you follow only one pattern of notes and presentation, so it will be easy for you guys to understand and assimilate, and write. You can derive easily in the exam. Okay, I hope you understood everything. Mahima, have you understood clearly?
Yes, sir, but I need to practice well. If I practiced
Yeah,
it
you
and
have, yes, yes. For any equation, we need practice. If you do it once or twice, okay. I will now tell one tip. Okay, before I conclude, I will give one tip. Tip is that for remembering these equations and any concept you want to remember, please correlate with the diagrams. Always you put your own diagrams, make own diagrams, and correlate so that you can remember that very easily, and you can reproduce in the exam. Now, one more technique is, there is something research has been done, mind power techniques. There are certain mind power techniques which I used to use in my MTech and PhD days. So what is that is, if you study anything now, today, you will remember for 24 hours. That's all. After 24 hours, your whatever you have studied will remain only some 8%. 8% of the memory will be there. That means your 92% it will be evaporate. That means you have to do one more revision after 24 hours of this. Maybe glancing, not full, but one full revision, and then just glance it, one more revision. So what happens is, now, if you, after 24 hours, if you do one revision, now that whatever you have studied will remain for 1 week. That means 7 days. Now what happens after 7 days? Again, you do one glance, not that full revision, but one glance, just revision, one glance, maybe some 10 to 15 minutes glancing. Once you do that, what happens now, that memory will remain for next 1 month. So if you continue this again after 1 month, if you do it, now next it will remain for 6 months. Your semester is 6 months. So you have to do revision how many times? One after 24 hours, one after 1 week, and one after 1 month. That's all. That means 3 times after taking. Now today class happened, so you do revision for next three times. That's all. As per I told, like, after 24 hours, after 1 week, after 1 month. That's all. That's it. You need not to study after that, because it will remain in your memory. But you have to plan and organize, because this is not only the subject, so many other subjects are also there. Accordingly, you have to adjust and correlate. So you have to do little work, homework is required. If you do it, if you plan it, then no one can stop you. You will definitely pass all the subjects with flying colors, more than 90%. I say you should aim for 100%. Some people say that you should score 70%, above 70%, 80%. No, I say you should aim for 100%. Why not 100%? Engineering also you can do it. I have done. Okay, I tell you, during my first year of engineering, there was a challenge. One of my student told me, because during our time it was year wise, not semester. Now it is all semester wise. Our time it was full year wise. At that time, we used to write exam, 25 exams at one stretch. Very, very, a huge pressure on our brains. But in that university level, anything if you score more than 55, 60 marks means university highest marks, year wise exam. Semester, now you have scope, you can score. That time I scored 80 marks out of 100, which was, I was the university topper for that subject. Because this was not only a challenge, it was actually my friends told, my two friends, they told, If you score 80, we will throw a party to you, something like that. So just because of for the party's sake, I scored 80 marks in that. Only one subject was. So that is how it is. So please try to score 100 out of 100. Then only you will get somewhere around some 70, 80. If you try to score 70, then it will come to you score 50 to 55, like 60%. So try to aim high. Then only will I be able to achieve the full marks. So, okay, whatever techniques I have told, whatever this thing, please use it and plan it. If you plan, so no one can stop, because this is your final year. Whatever you want to cover, whatever lakhs and whatever percentage you want to improve, please do it now only, because you will not get any other chance to improve it now after that, because you will regret this. Because I also thought like I will improve my percentage, but now it's not possible. So now you have chance. So whatever you want to throw full throttle, put your full pressure and do your best, and try to score 100 out of 100 in every subject by doing proper planning and your homework, whatever I suggested, the way revisions and all practices. Mathematics requires practice. You have to practice a little bit, but other things that klystron, reflex klystron and all, just glancing is required. For these equations and all, you require to little bit spend time. So please spend time. You will be able to pass with flying colors. Okay. Okay. With this, I conclude my talk today's presentation. So all the best. Have a nice time. Good day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.